Assalamualaikum and good morning, everyone. Hello, ada orang tak? Assalamualaikum. Okay, Assalamualaikum and good morning, everyone.
Good morning, sir.
Okay, so today we will continue on a bit about exercise that we have learned last week. I left exercise 4 for you, but I didn't give the answer. So today we will discuss about exercise number 4. Okay, so the question is evaluate the surface integral of f dot ds for f equals sine pi x y power of 3z and 4x plus z square over a surface of box from x minus 1 until 2, from y from 0 until 1, and z from 1 until 4. Okay, so when you find this kind of integral, you need to use um, divergence theorem. Okay, you need to convert this integral to divergence form. Okay, so let's write this. So you have this. So to find this, you can just find triple integral of divergence f. Okay. So let's find this part first, divergence f. So divergence f equals, so let's recap what is divergence. So it's simply a cross product from between the del operator and the vector f. So you get this answer, okay? Del f1 del x plus del f2 del y and plus del f3 del z. Okay, so let's look what is your f. Okay, so f is this vector. So let's differentiate each of these. Terguna. Okay, so let's differentiate each of these. Okay, so let's differentiate del f1 about with respect to x. So we get, so here we get del f1 is this one. So this is f1, f2, and f3. So f1 we have sine pi x. So differentiate with respect to x, we get pi cos x. Okay, and then plus del f2 del y. So f2 differentiate with respect to y. So we have y squared times z. So we differentiate with respect to y. So we get 2y times z. So we assume z as a constant. And lastly, del f3 del z. So we differentiate f3 with respect to z. So other variable becomes constant. So x becomes constant. So we differentiate z squared only. So we get 2z. So after you differentiate this, then you can evaluate this integration. So you can just write pi cos x. So dari pi sini. Okay. So now the volume is a box. Okay. So the question gives you the volume box. So you need to integrate within the box. Okay. So we can convert dv to dx times dy times dz. So let's rewrite this and include the range, okay, the range for x, y, and z as well. Okay, buatkan tempat baru lah. Okay, so we have pi cos pi x plus 2yz plus 2z. Then we differentiate, we integrate dx, dy, and dz. So here, this actually follows some order, okay? Meaning that you start integrate x first, after integrate x, then y, and then z. So for x, the value is put on the first integral here. So we have from -1 until 2. And then the second integral is for y. So we start from 1 until from 0 until 1. And then the last one is for z. So we start from 1 until 4. Okay, so we integrate x first. So integrate this with respect to x. So we get negative pi sine pi x over pi. Okay. Kena revise balik lah integration. Okay. And then we integrate the second function with respect to x. So here we don't have any x here, so it becomes a constant. So what happens if you integrate the constant? You just put x, okay? So you just put x, y, z. So the last one also has no x, so you just put x. So 2xz, and then substitute the value from -1 until 2 dy dz. So evaluate this thing first. So you can evaluate dekat luar, okay, kat tepi ke, kalau tak rasa macam tak nak serabut. So if you evaluate outside, so when x equals 2, so we get sine 2 pi plus 4yz plus 4z. And then minus 1. So just substitute -1 in x. So we get sine negative pi minus 2y. So sine pi is 0. Sine negative pi also 0. So we have 4yz minus plus 4z, sorry, plus 4z. So minus 2yz, so become plus. Minus 2z, so become plus 2z. So we get 6yz plus 6z. Okay. Harapnya betul lah. Then we just substitute this into the evaluation here. So we get integration 4110 for 6yz, 6z. So repeat the process for y pula. Okay, so integrate with respect to y. So here we have y, so it becomes 6y squared z over 2. And second one, we don't have y, so it becomes a constant, so it becomes 6yz. So from 0 until 1. Okay, so evaluate this. So substitute on 1 on y. So we get 6z over 2 plus 6z minus 0. Okay, so if you substitute 0, you get 0. So here you get 9z. Okay, if you evaluate this. And then substitute 9z into this. And then integrate with respect to z. So we get 9z squared over 2. Evaluate from 1 until 4. So kira kat tepi. So we get 9 over 2. 4 squared minus 1. So here 16 minus 1. So we get 135 over 2. Okay, so jawapan I dia 135 over 2. Okay, so the process is tedious. I think you can use calculator. Okay, you can use calculator to evaluate each of this integral without having to calculate manually. So if you look at your calculator, you have the function integration. Okay? My calculator is FX570ES Casio. So you have the integration. So if you integrate, you just use the integration and then put the variable that you want. Okay. But I'm not sure about integrating 3 times, but you can integrate one by one. Okay, so you can assume the non-x, for example, the non-x as the constant. Okay, like y, z, like the first integration here, you can assume y and z as a constant. Okay, so if you don't know how to use calculator, please Google. Okay, so in exam, I don't expect you to calculate panjang-panjang lah. Okay, buang masa panjang-panjang. If you find the answer straight away from calculator, symbol lab ke, okay je. Okay. Okay, any question before we proceed with new topic, new lecture? Okay, so this question for midterm, so lecture 2C will not come out in midterm, okay, but will come out in final. So your midterm will cover vector, one question from vector. Actually, one part of question from vector, and another part is from matrix. Okay, so from vector, basically you need to understand how to do scalar product, cross product. Okay, benda tu je. And then for matrix, you have to understand how to find eigenvalues and eigenvectors. Okay, because these two things are the most important in continuum mechanics. And for lecture 2C will come up in final exam. Okay. Okay, so let's continue with another lecture today. So I have explained to you for the past 3 weeks about the mathematical background. So maybe some of the mathematics you have familiar, but some of them are new to you. But I hope you can understand. Okay, can study. If you don't understand, you can just ask me anytime. So now let's go into the real part, okay, for the continuum solid mechanics. So the first part that we need to understand before we go into details about continuum solid mechanics is to understand how to describe motions. Okay, so if we want to describe the deformation of something, like deformation of plasticine ke, deformation of a ball, for example, we need to understand how we can describe the motion of each point in the object. Okay, so before we go into detail about understanding the deformation or the stress distribution in an object, we need to understand first what is the motion, how to describe the motion. So in this topic, you will be able to understand the concept of configurations and frame of reference, and then also understand the concept of mind map, of motion map, motion map. And then understand the concept of deformation and description, and also understand the concept of displacement, velocity, acceleration. So I think you have learned this in statics, dynamics, displacement, velocity, acceleration, but define this in different coordinate description. Okay, so what is description? Later on we will see, and also understand the concept of material time derivative. Okay, so before we go into detail, let's look a bit about what is actually continuum mechanics. Okay, so a matter usually consists of atom. Okay, so in atom we have electrons, protons, and neutrons, and the electrons can form chemical bonds with another atoms. So to study the mechanics of atom, like at atomic level, is actually very useful. But if you want to study the bigger picture of deformation of solids, for example, deformation of papan ke, deformation of bangunan ke, you don't need to understand atomic level, okay? But many people or many researchers actually study atomic level to investigate something else, okay? A more detailed understanding about how atoms behave. So the representation of material as atoms, we can use discrete representation. So discrete is meaning that the data is not continuous. Okay, continuous maksudnya dia bersambungan. Okay, dia tak ada there's no void, tak ada void in between a material. So discrete material means that we can see voids ataupun ruang in between the materials. Okay, so continuum mechanics basically concerned with study of matter at a bigger level, at microscopic level, by assuming that the material as a continuous body, okay, which has continuous mass, and ignores the atomic structure. So contohnya kita nak study deformation of metals, for example. So we know that in metals there is metallic atom. Or sometimes if you use alloy, you know that in alloy we have different kinds of atom, like cobalt, chromium, for example. We have cobalt, we have chromium, and maybe their sizes are different. So there are voids in between them. But in continuum mechanics, we don't assume the existing of the voids. Okay, we assume that the material is continuous ataupun dia punya particle dia size yang sama. Okay, so in continuum mechanics, an object is no longer assumed to made up of finite set of atoms, but it consists of infinite number of material points. Okay, so we can assume that a material for a continuum mechanics is made up of a lot of points. Okay, banyak-banyak point yang halus, yang kecil, yang rapat antara satu sama lain. So this is an example of the difference between continuum model and discrete model. So continuum model, we can assume that the model is selanjar lah, okay, continuous, bersambungan. But for discrete particle model, we can actually see the particles in the material. So these two different modeling approach. Dia punya mathematical model dia different lah, okay? Dia punya procedure, the numerical method dia berbeza. And sometimes researcher tries to overlap these two different modeling approach. Okay, so for the discrete particle approach, usually it will take more computational power. Okay, because you have to model each of these particle. So each of the particle has different behavior. But for continuous model, we can assume that the whole particle or the whole material has similar material properties throughout the body. So before we go into detail, so let's look at the concept of configurations. Okay, so let's assume a potato. Okay, so ada kentang. So kentang ni, let's say awak baling kat kepala kawan awak, so dia kemik macam ni. So in this kentang, in this potato, we can assume that this potato consists of a set of particles. Ada banyak particles yang rapat-rapat, okay? Tak ada rongga lah. So we can assume that at initial condition here, at initial stage here, we call this initial stage as the reference or undeformed configuration, okay? Konfigurasi asal ataupun konfigurasi tidak berdeform, tak tahu bahasa Melayu. Represented by, so the particles can be represented by the intersections between the horizontal and vertical line. So setiap horizontal and vertical line here, the intersection points here can represent each particle, macam mesh lah. Okay, if you learn finite element method, you can assume that each node in the mesh represent the particles. So after you baling potato ni kat kepala kawan awak, then the potato becomes deformed, okay, or change in position. So after the deformation, each of the particle now occupy a new position. Okay, dia bertukar tempat. Okay, contohnya dari position ni, sekarang dia bertukar ke position sini. Position ini contohnya, dia bertukar. Okay, it change in position. So the new position here, we call it as the current or deformed configuration. So we have two types of configurations. We have reference configuration and we have current configuration, or we call it undeformed configuration and deformed configuration. So the motion of each particle depends on the behavior of the potato. Okay. So kalau potato ni keras, bila baling mungkin dia tak kemik. So the particle will not move lah. It will stay intact at original location. If the potato is lembik, then if you baling, then each of the particle will change in location. So when change in location, then there is a deformation. Okay. So in mathematical form, we can further describe the two different configurations. Okay, so let's look at the reference configuration first. So at reference configuration, we say the body or the jasad or the potato just now at reference configuration using the symbol omega naught. Okay, omega naught ataupun ohm naught. So at time t equals 0, so at time t equals 0, the body is at reference configuration. So the position, let's say the position of the particle x here can be described using vector. Okay, so the position of this particle x can be described using vector by assuming the original coordinate exists. Okay, at origin. So we represent everything at reference configuration using big symbol or big capital letter. So here we represent by a big X symbol. So at reference configuration, it is also referred as initial configuration or material configuration and also undeformed configuration. So dia ada banyak nama. Okay? So let's say if question says initial configuration, so it means reference configuration. So the particle x here can be represented by a vector. So we write the vector using symbol big capital X. So in computer we can bold, make it bold. So vector x equals xi times ei. Ei here is the ijk. Okay? E1 is I, E2 J, E3K. So in our lectures or in our class, we use E1, E2, and E3. So you have to remember for reference configuration, we use capital letter X, big X. Now let's look at the current configuration. So now let's assume that the body omega naught here is now deformed after you throw the potato. So it deforms, so it can either move or rotate or change in shape. So it deformed into a new position. So it becomes, it change shape and deform into this new current configuration. So at time more than 0, maybe time 1 ke, time 2, and so on. So now the position of this particle X here change in position, okay, ditukar position. So it now occupy a position small x here. So for current configuration, we use small letter, okay. So reference configuration, we use capital letter. So current configuration also known as the deformed configuration. So we can represent the particle small x here by a vector. So small x equals small xi times ei, and measured at the same coordinate, okay, same coordinate system. So the motion that change the material from reference configuration to current configuration is known as the motion map. Okay, so the motion map is represented by the symbol x lengkung sikit. So x lengkung ni we call it chi. Okay, chi. So the motion map chi describes the motion that carries the points in x, the point x located in at the current configuration to a new position in the current configuration. So we can write in function, we can write in mathematics, x small x equals the function chi of x, big X, and time t. So to relate between small x and big X, it is related by this function chi of x and t. So the motion chi is assumed to have continuous derivative, okay? Meaning that kita boleh differentiate x, okay? So that's the meaning of continuous derivative. And the motion chi also can be okay? Can be invertible. So if you want to find the position x, big X from position small x, you can just inverse, okay? So to find big X, just inverse the function and then gantikan dengan small x. So later we will see more example. Okay, so now let's look at an example how this is applied. Okay, so let's say you are given a motion of a body described using the mapping chi. So mapping chi x and t equals x. So describe the position x. So the new position x equals x1 plus 80x2 E1 plus x2 minus 80x1 E2 plus x3 E3. Okay, so ini vector yang baru lah, okay, for x, for small x. So let's say a question asks you to find the new position of the points 0, 0, 0, 1, 0, 0, 0, 1, 0, and 1, 1, 0. So what you can do is simple. You just substitute this point into the mapping chi. So if you substitute 0, 0, 0, so the new position becomes 0, 0, 0 if you substitute into this equation. So it happens that if you substitute 0, 0, 0, the new position tak berubah. Okay? It's the same position. But at point 1, 0, 0, the new location becomes 1 minus 80, 0. So dia macam berubah dekat y-axis. And then point 0, 1, 0, if you substitute, it becomes 80, 1, 0. So dia berubah dekat x-axis. And then lastly, 1, 1, 0 becomes 1 plus 80, 1 minus 80, and 0. So dia berubah location. Okay, so as simple as that. If you are given initial points and you want to find the new configuration point location, just substitute, okay, into the mapping. So now let's go into a more complicated example. So let's say for the same mapping, you are asked to sketch, okay, sketch the new position of this point, of the similar point at different time, okay. So at 4 different time points and for the same points given earlier. So you have found the current configuration or current position, okay, from previous slide. So now you just substitute the time and also the value of A or any value given to you. So just substitute into this. And then you just sketch, okay? So the garis putus-putus ni represent the position of the points at time 0. And then at time equals 1, the position represented by the white box here, dia macam terrotate sikit, okay? And then at time equals 2, the square is rotated more clockwise, okay, but dia macam elongate sikit. And at time equals 3, the material rotated more clockwise and elongates more, okay, in both sides, on both sides, okay. And at time t equals 4, dia membesar lagi dan rotate lagi. So if you, let's say you are given a question asking you to sketch, you just substitute the point into the mapping and the time point, okay, at the time, and then just sketch macam biasa je, ikut je value ni bila dah substitute. Okay, lukislah koordinat dekat kertas jawapan. Okay, you can try this later. So the answer is already given here. And then similar mapping, but now we want to invert the mapping chi. So you have x, small x in terms of big X, but now you want to find the big X in terms of small x. Okay, so you have to invert the mapping. So invert the mapping is slightly problematic lah, because the mapping is in terms of function. Okay, so you cannot invert using calculator. So boleh invert pakai symbol lab, okay, kalau exam online. So firstly, arrange the matrix chi in matrix form. So you can write x1 equals x, big x1 plus 80, big x2. Small x2 equals big x2 minus 80 x1. And then x3, small x3 equal big x3. So you can write this in matrix form. So the idea here is to get x1, x2, x3. So now your equation is you find x1, small x2, and small x3. But now you want to find big x1, big x2, and big x3. So you have to invert this matrix, bawa dia pergi sebelah. So to invert this matrix, you have to use the inverse of matrix formula. Okay, so you can try this later, okay? How to inverse the matrix. Okay, so let's say you are given this question here, you are given x1, x2, and x3, big X. So let's say what happens if you are given small x1, small x2, and small x3. So let's say 3, 5, 3. So find x1, x2, and x3. So what you can do is you invert the mapping, or you solve the equation simultaneously to get x1, x2, and x3. Okay. So soalan macam ni ada dalam test. So try to understand the concept of inverse the mapping. Okay. Okay, so let's look at this exercise. So given the motion of a body, so x1, small x1 equals alpha big x1 plus beta big x2. Small x2 equals beta x1 plus alpha big x2. Small x3 equals big x3. So find the inverse of this motion. Okay, so the question wants you to find the inverse. Okay, you want to find the inverse of the motion, and you have to find um, the um, the motion, the value of big X. Okay, so let's write this in matrix form. So x1, x2, x3. So this is alpha, beta 0, beta alpha 0, 0, 0, 1. So you want to inverse this matrix here. So to inverse, first you find the determinant. So determinant of the matrix chi equals alpha times alpha minus beta times beta. Okay, so you know how to find determinant. Okay, so try later. So you get alpha squared minus beta squared. I hope this is correct. Okay, and then after you find the determinant, you need to find the cofactor. Okay, matrix cofactor of chi. Okay. Um, so the first cofactor here becomes alpha, and second it's beta minus, and then third one 0, and then this minus beta alpha 0, 0, 0 alpha squared minus beta squared. Okay, so later you can check using symbol lab. Okay, then the inverse of chi, just the determinant times the cofactor. Okay, but soalan yang susah-susah macam tak ada lah. Okay. Usually the question is straightforward, so bikin fikir-fikir sikit. Okay, now you have to look at how to define the motion between two configuration, reference and current configuration. So because of these configurations, kita ada dua cara. Okay, we have two ways to look at deformation. Okay, one way is looking a deformation using material description, or what we call Lagrangian description. And then another way is looking at a deformation using spatial description or Eulerian description. So what are these? So these are the description of deformation. Okay. So let's look at the material or Lagrangian description. So in material description, the motion of the body is always referred to a reference configuration. Okay. So kita lihat the motion of a body from reference, okay, from a point of reference. Kita meaning that we look at the motion or the motion of that body based on the body at reference configuration. So it is similar by visualizing a motion or a movement of something as if you sit on a boat. Okay, so you duduk dalam boat, you bergerak dekat sungai. Okay, so then you calculate your motion. Okay, you calculate as whenever you are still in the boat. Okay, so you will feel that you are not moving, but you will feel that your surrounding is moving. Okay, so the motion of the particle is observed by following the individual particle as it moves through space and time. And then another description is spatial or Eulerian description. So in spatial description, the motion of the body is referred to a current configuration. So kita tak refer the deformation from the original configuration, but we refer the deformation from a current configuration. Okay. So this can be visualized by you sit on a river. Let's say ni sungai. So you duduk sini, and then you just look the particle moves. So this is spatial. The other one is you observe the motion as if you duduk dalam boat. Okay, you duduk dalam particle tu. So you gerak. But ni you duduk fix dekat satu tempat. You tengok partikel tu bergerak dekat tempat yang you tengok saja. You tak tengok ke tempat lain. Okay. So the motion of the particle is observed by focusing on the same location, okay? On the same specific location, and you count. Okay, you count how many particle pass through that location. Okay, so we have two ways of measuring motion. If you baca pasal recent news yang mengatakan matahari ni sebenarnya bergerak juga. Okay? Bila matahari bergerak, selama ni kita belajar yang matahari ni duduk setempat je, berputar pada paksi dia, pada satu tempat saja. Selama ni kita belajar salah. Yes, memang matahari ni sentiasa bergerak, tapi dia bergerak mengelilingi the galaxy. Okay? Tapi pergerakan dia mungkin sangat slow lah. Okay? And then ada orang kata matahari juga bergerak sebenarnya mengelilingi bumi. So bukan bumi mengelilingi matahari. Sebenarnya ini adalah dipanggil konsep relative motion. Macam mana kita lihat motion tu? So kalau kita lihat motion tu sebagai matahari tu mengelilingi bumi, logik juga matahari mengelilingi bumi sebab kita fix dekat bumi, kita duduk dekat bumi. Tapi kalau kita duduk dekat matahari, kita akan nampak bumi tu mengelilingi matahari. Okay, so this is the concept of spatial and material configuration or description of motion. It is based on where you locate yourself. Okay, so if you locate yourself in that particle and observe the motion of that particle as you move along the particle with the particle, that is the material description. So if you observe the motion of the particle by sitting statically at a point, at a location, so you are observing the motion of the particle spatially. Okay? Okay. So why there are two? So Lagrangian versus Eulerian description. So a fluid flow field can be thought of as ada banyak particles. So mathematical laws can then be written for each fluid particles. Setiap fluid particle ada dia punya mathematical law dia. So this description is Lagrangian or material. Another view of the fluid motion is using Eulerian description. So in the Eulerian description of fluid motion, we can consider how the flow properties change at the fluid element. So we take a control volume or a box here, control box, fixed in space, and then kita kira berapa banyak partikel lalu dalam box ni. So this description is Eulerian. So we fix a position, then kita kira berapa banyak particles moving into this box, moving in and moving out. And then we can derive the governing equation and so on. Okay. So this is another way of looking Lagrangian and Eulerian. So for the Lagrangian, each of these point in the circle here change position. Okay. So we observe the motion of this point here by measuring the position of each point at a new location. Okay, kita kira setiap point ni from original and to the new location. But in Eulerian analysis, kita letak satu kertas graph ke, and then when this object change in position, kita just kira berapa banyak point dekat point yang asal, dekat kertas graph yang asal, berapa banyak point yang lalu dekat setiap titik dalam kertas graph tu. So kita tak kisah point yang baru tu datang dari mana. Kita hanya kira berapa banyak point dalam that specific location. Okay, so all of this actually if in software, in finite element software, dia dah handle kan. Okay, there is a code okay written for this. So you don't have to worry about macam mana nak kira ni dalam software ke, dalam tak pakai tangan ke. But we still need to learn. Okay, so in Lagrangian description, the current coordinate x can be expressed in terms of reference coordinates x, big X. So this is the original mapping. Okay, so to find the small x, you just describe it by using the mapping chi. So this is the material description. Okay, so to find the point x, small x, just substitute the point big X into the mapping. So in case if you have a variable phi, let's say this variable measures the temperature or pressure of that particle. So this variable can be described with respect of reference configuration big X. Okay, so phi equals phi, just substitute big X and time t. Later on we will see more of this. And then in Eulerian description, the motion is described with respect to current configuration. So big X equals the inverse of mapping chi. So in case if you have a variable phi, so you want to describe this in spatial coordinate or spatial description, so you just substitute small x, okay, and t. Okay, so that's all about description. Okay, soalan tu aja teori. So in your exam, there is no theoretical question like describe what is Eulerian, Lagrangian. Okay, tak ada soalan macam tu. But that thing will be used quite a lot in coming lectures lah. Okay. So now let's describe the displacement. Okay, we have described the position of the reference position and also the current position of a particle. But how to measure the displacement of that particle? Okay, the displacement of that particle from reference configuration to the current configuration. So again, we can use vector. Okay, so the displacement u is basically this vector measured from big X to small x. So we can relate these three vector, big X, u, and small x using a vector relationship. Okay, so big X plus u equals x. Okay, so this one use yang triangle that I shown in week 1. Okay, so this you can rewrite as this. Okay, so this x here can be written in terms of mapping. Okay, mapping chi. So that's why here you get x plus big U equals the mapping chi. So to get the displacement, U equals mapping minus x, or small x minus big X. Okay, so this is the displacement of each particle. Okay, so that one is in Lagrangian, still in Lagrangian description. So now we can find the velocity and acceleration. We have the displacement, then we can find the velocity and acceleration. So to find the velocity, you just differentiate the displacement with respect to time. And then to find the acceleration, you just differentiate the velocity with respect to time. Okay, simple. So first you need to find the displacement, then you can find the velocity and acceleration. So these are in Lagrangian. So whenever you see big capital letter, it means that it's in Lagrangian. Okay. So now we want to describe the displacement, velocity, and acceleration in Eulerian description. Okay. So in a small letter, okay, small u. So just now from this figure, we know that big U equals small u. Tapi in terms of what? Okay, so macam big U, it's in terms of big X. But small u, it's in terms of small x. So to get big small u, you just take small x minus big X. So big U, the big U just now, it's the mapping, minus big X. Meaning that you need to use the mapping. Okay. But to get small u, you just use the value X. Okay, tak perlu guna mapping. Later on, we will see example. What is this meaning? Okay. And then to get the velocity, you can do substitution. Okay. So the two description of displacement can be related by, let's say U, the big U, displacement material, Lagrangian. You want to get displacement in Eulerian, you just substitute the big X here with the inverse of the mapping. Okay, to get in terms of small x. Okay, meaning that the big U here, dia punya equation dalam bentuk X, big X. Tapi dalam small U here, dia punya equation dalam bentuk small x. Okay. And then to get the velocity, so this is the velocity in Lagrangian. So to get the velocity in Eulerian, so in Lagrangian, it is in terms of big X. So to get in terms of small x, you just substitute big X to get small x. Later we will see example. So here, the procedure is the velocity and acceleration in Eulerian can be found by calculating the velocity and acceleration in Lagrangian and then substitute using the inverse of the motion. Okay. So ada dua proses lah, to inverse the motion and then substitute into the Lagrangian velocity and acceleration. So let's look at an example. What is this means? Okay. So given a motion of a body in material description, okay, so x1 equals exponent t big x1 minus exponent minus t x2 big x2. Small x2 equals exponent t x1 plus exponent minus t big x2. x3 equals big x3. So assume t bigger than 0. Find the velocity and acceleration in both material and spatial coordinates, or in Lagrangian and Eulerian description. So let's find in Lagrangian description first. So firstly, you can invert the motion, okay? Or you can write the motion in terms of matrix first. Okay, so you write this motion in terms of matrix. Then you can inverse. Okay, you can inverse the motion. Okay, so you inverse, you get x1, big x2, big x3 in terms of small x1, small x2, small x3. Okay, you inverse. Okay, so try inverse yourself later, by yourself later. And then to find the velocity, so v, the big V, is basically you differentiate the mapping about time with respect to time. So to find the material velocity, the material description velocity, so you differentiate this mapping with respect to time. Okay, so what happened is that, let's say if you want to find V1, so you differentiate del x, x1 t with respect to time. Ataupun senang tengok dari sini lah. So to find V1, you differentiate del del mapping with respect to x1, differentiate with respect to t. Okay, so meaning that you differentiate this first equation here with respect to time. So you get, but x1, okay, sorry, tak ada x1. So you differentiate the mapping with respect to time. So you get differentiate this with respect to time. So you get exponent t x1. Differentiate this with respect to time. So ada minus, you bring minus ke bawah. Okay? So you get plus et, e minus t, x2. Similarly, for V2, differentiate the motion number 2 here with respect to time. So you get et, x1, minus e minus t, x2. And similarly, for V3, tak ada time, so it becomes 0. Okay. So differentiate x3 with respect to time. So x3 is another variable. There is no variable time, so you assume x3 as constant, so it becomes 0. So that's why here you get this answer. And then to get the acceleration, simply differentiate the velocity with respect to time. So here a1 del v1 del t. So you get et x1. So here becomes minus e minus t x2. So similarly a2 et x1 plus e minus t x2. Okay, so differentiate this. And then a3 zero je sebab memang velocity dah 0. Okay, so you get the velocity and acceleration in material description. Then now you want to find the velocity and acceleration in spatial description. So what you can do is you just need to convert all of the big X here to small x. Okay, so by substituting the inverse of the motion. So you have found the inverse of the motion. So just substitute x1, x2, and x3 into v1, v2, v3, a1, a2, a3. Okay, so just substitute. Okay, so v1 equals x2, v2 equals x1, so v3 equals 0, and then a1 equals x1, small x1, a2 equals x2, a3 equals 0. So you just substitute the inverse into this, into the material velocity and acceleration. Okay, now let's look at this exercise. So given the motion of a body, this is the motion, and then find the displacement, velocity, and acceleration in terms of material spatial coordinate. So let's find the displacement first. So displacement for the material coordinate. See, for material, so big U, so big U1 is just the mapping minus x1. Okay. So the mapping number 1 is alpha x1 plus beta x2 minus x1. So you get alpha minus 1 x1 plus beta x2. So similarly, u2 mapping minus x2. So take the second x2, the second mapping. So beta x1 minus alpha x2 minus x2. So you get beta x1 minus alpha plus 1 x2. Okay, macam ada salah somewhere, but it's okay. And then for u3, it's just the mapping minus x3. So you get 0 displacement. Okay, betul lah, sebab the point 3 here, dia fix dekat position asal je. Dia tak bertukar position. So the displacement is 0, okay. The displacement of the point at the third vector, okay, at the third coordinate number is 0, it's fixed, okay. But the displacement for the remaining 1 and 2, it has displacement. And then from the displacement, you can find velocity. Okay, there are two ways you can find velocity. You can either differentiate the mapping, or you can differentiate the displacement. So V1, you just differentiate the displacement. So del U1, del T. So from here, oh, there's no T. So velocity dia 0. Dia tak ada T. So similar to V2, del U2, del T. So there's no T here. So everything is constant. Okay. So there is no velocity number 2. So V3 also 0 because the displacement is 0 already. Okay. So same with acceleration, acceleration also 0. Okay, soalan ni ada something wrong, tertinggal T somewhere. But it's okay. Let's say your question has T here, so the T. So maybe later you can try by yourself to find the velocity and the acceleration. And then also find the velocity, spot velocity in spatial, okay? Just try by yourself later, okay? So you need to use the inverse mapping and substitute into V1, V2, V3, A1, A2, A3 to get the spatial velocity and acceleration. Okay, so lastly is about the material time derivative of a material field. So this is another thing that is important actually. So the reason why we need to find this is, let's say assume that you have a swimming pool here. So kita guna konsep swimming pool. So let's say dekat sini temperature dia tinggi, temperature water kat sini tinggi, and the temperature dekat satu hujung lagi rendah. Okay, so if you swim from temperature tinggi to temperature rendah, then you can feel the change in temperature, okay, in the water temperature. So that you feel the change of water temperature as you move, okay. What happens if you stay in the middle of the swimming pool, and then let's say the temperature at this point here berubah disebabkan external environment ke ataupun air tu semakin menyejuk ke. So you are not moving, you're fixed at a point at the location, but the temperature is changing, okay, at that position. So there are two ways the temperature is changing. One way is if you move, then the temperature is changing from one location to the other location. Another way the temperature is changing is if you stay at a position and then the temperature at that position changes. Okay, there are two ways of measuring the change in temperature. So temperature ni is a scalar value, okay, compared to the position just now, the position x1, x2, they are vectors, okay. So scalar value also change with respect to either material description ke or spatial description, okay, similar to position tadi. So let's say for a variable phi, for example, the temperature, and this is known or measured in the material description. So phi is in terms of big X and time. So if you want to find the differentiation or derivative of phi, so you just simply find the derivative, assuming the x is fixed, okay, fixed value of x. So the material time derivative represent the rate at which the phi changes with time, while keeping the coordinate, the reference coordinate fixed. Okay, you don't change the reference. So you can also find the time derivative, material time derivative of a spatial field. So let's say if you have a phi in spatial description, so instead of big X, the phi is in small x. So the total time derivative is given as, so you have to differentiate the phi and then plus the velocity times the differentiation of phi with respect to x, or v times the gradient of phi. Okay, so this is gradient. Okay, if you go back to lecture 2C, you need to find the gradient and then dot product with the velocity, big velocity, okay, material velocity. Ini complicated sikit lah nak kira. So V is the velocity in the material description. So another way to find the material time derivative of spatial field is by substituting the inverse of the motion into the material time derivative of material field. Okay, sama macam velocity tadi. So to find the velocity in spatial description, you just substitute the inverse motion into the velocity in the material description. So there are dua description of velocity. Okay, as I said earlier, it is based on where you locate yourself in observing the position, okay, or the velocity or the temperature and anything. Okay. So why we need this material time derivative for spatial field? So as I said just now, we use the concept of swimming pool just now. So a swimmer at one point in a lake sense the water temperature change at that point from morning to evening. Okay, so let's say korang berenang dalam swimming pool dekat satu tempat berendam je dari pagi sampai petang. So boleh rasa air tu dari sejuk jadi panas, jadi sejuk balik. Okay, so the water becomes warmer due to heating from the sun. So this is represented by del phi over del t. So imagine the lake has high water temperature at one end and then lower water temperature at the other end macam tadi. And then you swim between these 2 points, okay? Or berenang dari kawasan yang high temperature to lower temperature. So you can see or you can sense there's a change in water temperature. So this change in water temperature is represented by this V, velocity V, material velocity, dot the gradient of the temperature. So ada dua jenis temperature lah yang measure at how you move or how you locate yourself. Okay. So let's look at an example. So the motion of a body can be described by this mapping, and the temperature in the body has the spatial description. So temperature in spatial description in small x, okay. So dia bukan dalam big X. So T small x equals x1 plus Tx2. So find the velocity in material description. And then find the time rate of change of T in both material and spatial description. So first, let's find the velocity in material description. So meaning that kita nak cari big V, okay. So to find big V, just differentiate the mapping with respect to time. So let's look at how to answer this. Okay, sorry, ni salah ni. This is actually a big V, okay? So big V, you just differentiate X with respect to time. Okay, V1, big V2, big V3. Okay, so you differentiate the spatial. So differentiate x1 over dt, x2 over dt, x3 over dt. So let's look at this thing first. So let's say if you want to find v1, so differentiate the mapping, this mapping with time. Okay, so you differentiate this part only. So if you differentiate this with time, so you get a x2. Okay, because x1 tak ada t, so dia constant. And then to find v1 and v2, again you differentiate the second point here, the second vector here with respect to time. So here x2 is a constant. So here kita ada time, so we differentiate this section only, so we get minus a x1. And then lastly v3, so tak ada time, so it's just 0. Okay, okay, so you get this. And then to find the time rate of change of temperature, so basically you nak cari the material T in material dispersion. So you are given the T in spatial dispersion in small x. Okay. So what you can do is you substitute the inverse of the mapping, or you substitute the mapping into x1 and x2. So sekarang ni kita ada x1, small x1 and small x2. Kita tak nak dalam bentuk x1 and x2 ni, kita nak dalam bentuk big x1 and big x2. So you just substitute x1 and x2 using this one. Okay, so this is x1 and this is x2. Just substitute this into this x1 and x2. When you substitute, you get this temperature in material description. And then to find the time rate of change of temperature in material description, you just differentiate this with respect to time. So you get negative 2at x1 plus 1 plus a times x2. Okay. And then to get the time rate of change of temperature in spatial description, you just use the formula given earlier. Okay, so you differentiate del T big T over time. So this is in spatial. So del T with respect to time, differentiate temperature with respect to time. You get x2. Okay. So this is big V. Silap kat sini. And then we find the gradient of temperature. So this is the formula for gradient. So gradient of temperature, you will get a vector. Okay. So later you can refer to lecture notes on gradient. Okay. So del T del x1 E1 plus del T del x2 E2. So del T del x1 becomes 1 equals 1 times E1. So you get E1 here. Del T del x2. So differentiate ni terhadap x2. You get T. So you get T E2. Then you substitute into this equation here. So d dt, T in spatial, just substitute. Okay. So ni equals just now ini. Okay. Okay, so you get this answer. Oh, sorry, dia tertinggal satu. So you need to V dot del T. So V1, V2 tadi, itu negative AX1. So we have AX2 dot dengan E1 plus negative AX1 dot dengan TE2. So here you get this part here. Okay, del T yang ni. So X2 plus ni. AX1, AX2. Ni ganti balik X2 dari sini. So X2 ialah ni. So instead of writing X2 here, you can write X2 minus AT X1. Okay, sama. So just substitute here. And then this is after you simplify this section here. And then tambahkan. So negative AT X1 minus AT X1, you get 2 AT X1. And then X2 plus AX2, you get 1 plus AX2. Okay. So there's an exercise here. We will discuss this next week. Okay, inshallah. So you can try first this exercise. Okay, so this is just an additional note. So there are two types of motion. So we have steady motion. So steady motion is when acceleration is 0. Okay, so when acceleration is 0, then the motion is steady. Then a uniform motion is when the velocity is independent of position x, or the gradient of velocity equals 0. Okay, so this is just tak keluar exam lah. Okay. So just nak beritahu yang steady motion, the acceleration is 0, and then the motion, uniform motion is when the gradient is 0, the gradient of velocity. So that's it. So one of I think 2 questions for midterm coming out from this topic. Okay. Bukan dari exercise 3 lah, exercise 3 tak keluar. So it will come out from somewhere dari velocity ke, it determine velocity, acceleration, or something that requires you to sketch. Okay, like this one. Okay, sketch the new position of a material. So two questions come out, one from sketching and one from calculating the velocity. So I hope you can study for this. It's a bit difficult, but the calculation is difficult, but the concept is okay, good. Okay, and starting next week, all of this will be used again, but in a different way. We will look at how to measure the deformation, and from the deformation we get strains. Okay, and there are a lot of new terms, okay, that you never learned before, but the calculation is quite straightforward, but the process to get the answer is maybe berliku-liku sikit. Okay, similar to like example 5, for example. Okay, dia punya calculation is a bit complicated, tapi the calculation is straightforward, but the process is a bit complicated. So just to remind you, now it's week 5. So your test, midterm test, is in week 7. Okay, so we have one more week next week to cover the topic. So in week 7, we are going to have our midterm test. Okay, So that's it for today's class, and see you again next week, inshallah. Assalamualaikum. Goodbye.
Terima kasih, sir.